Hello everybody. Today we're going to learn how to combine vertical and horizontal transformations. In class on Monday and Tuesday we strictly worked with vertical transformations and then strictly worked with horizontal transformations. Okay, so the way this works is given a function f of x, we can form the graph of y equals c f of a times x minus b plus d, and that's going to be the graph of f. Number 1, first you're going to scale horizontally by a factor of 1 over the absolute value of a. So what this means is that when you're transforming points of the graph of f, you're going to multiply each of the x coordinates by 1 over the absolute value of a. If the absolute value of a happens to be between 0 and 1, the scaling is going to give a stretch. And if the absolute value of a is greater than 1, the scaling actually gives a compression. Step number 2, if in addition the value of a is less than 0, the scaling is followed by a horizontal reflection. In that case, you would multiply all the x coordinates of the graph by -1. Once the scaling factor a has been taken care of, the next step is to form the horizontal shift given by the value of b. You would then shift the graph absolute value of b units right if b is greater than 0, and absolute value of b units left if b is less than 0. Notice that these first 3 steps give you all of the horizontal transformations that are possible. And these are just the exact same 3 steps that we learned on Monday and Tuesday. Once we have finished these first 3 horizontal transformations, the next 3 steps would be to start doing our vertical transformations. You would look at the c in front of f, and we would want to scale the graph vertically by a factor of absolute value of c. This is the point where we would just multiply all the y coordinates on the graph by the absolute value of c. Now after the vertical scaling by a factor of absolute value of c, if c happens to be less than 0, we're going to follow that scaling by a vertical reflection. In that case, we would multiply all the y coordinates on the graph by -1. And finally, once the vertical scaling and possible reflection have taken place, capital D is going to tell us to shift the graph up absolute value of d units if d is greater than 0, and shifted down absolute value of d units if d is less than 0. What this does in effect is if d is positive, we're just going to add d to the y coordinates, and if d is negative, we are going to be subtracting from the y coordinates. Okay, now that we've seen all the steps involved in a transformation, and we know how to combine the vertical and horizontal transformations, let's do a graphical example before we decide to do an algebraic example. So, given the graph of the function f on the right, this is the same graph that we were working with in class on Monday and Tuesday when we viewed the vertical and horizontal transformations separately. What we want to do is given that graph f, we want to graph the function g of x, which is 2 times f of, in parentheses, -2 times the quantity x minus 1, parentheses, plus 2. Okay, so I believe that it's always a good idea when you're given the transformation of a function f to write down the corresponding capital A, capital B, capital C, and capital D. Okay, so for this example, alright, something funny happened with my recording, but let me repeat the problem. We are working on the first example, and given a function y equals f of x graphically on the right hand side, we want to graph this function g of x given by 2 times f of, in parentheses, negative 2 times the quantity x minus 1, right parenthesis, plus 2. Okay, so I always think it's a good idea to find the corresponding values of capital A, capital B, capital C, and capital D. So what we'll do is notice the value inside the parentheses. The value for A inside the parentheses would be negative 2. That would be this value right here. B is going to equal positive 1. That's what we are subtracting from x inside the parentheses. The value that we are multiplying f by out front, capital C, is going to be positive 2. And then finally what we're adding to the output of f at the end is going to be a positive 2, so D is equal to 2. And then using these values of capital A, capital B, capital C, and capital D, we're going to transform each of these 4 points that make up the endpoints of each of the line segments in the graph of f. Okay, so what I've done now is that we've identified those 4 points that we're going to transform. This is kind of the way I like to transform points on the graph of a function. If you read the textbook, you will notice that oftentimes they will put the points in a table of x and y values, and then they will work with transforming those coordinates from there. But I like to first list my specific points that I'm going to transform, and then I will draw an arrow to the next point in the series of transformations. For instance, looking at the value of capital A, which happened to be negative 2, we know that in step 1 we are supposed to horizontally scale by 1 over the reciprocal of the absolute value of A. And then since A is negative, we're also supposed to follow that with a horizontal reflection. Now, you can combine the horizontal scaling and the reflection in the same step by just multiplying all the x coordinates by the reciprocal of A. The reciprocal of A is negative 1/2, and multiplying all of your x coordinates by negative 1/2, for instance, negative 2 times negative 1/2 is going to give you a new x coordinate of positive 1. Multiplying 0 by anything is going to leave you with an x coordinate of 0. And multiplying this positive 2 over here by negative 1/2 is going to give you this negative 1 on the right, and multiplying positive 4 down here is going to give you a new x coordinate of negative 2. Okay, now when you're following the transformations that are given by capital A and capital B, since those are horizontal transformations, you're going to notice that it's only going to change your x coordinate for now. The y coordinates won't change until we apply the effects of capital C and capital D. Okay, so now that we've taken care of the scaling factor capital A, which actually this time gave us a scaling and a reflection, notice that again all the x coordinates were multiplied by negative 1/2. What this is doing is we're going to get a compression towards the y-axis. Notice the absolute value of A is greater than 1. If you look back at the beginning of the video and follow the rules for each of the steps, you will see that you always multiply the x coordinate or scale by 1 over the absolute value of A, and then follow that with a horizontal reflection if A happens to be negative. Okay, so now what we're going to do is take a look at the effect of capital B. So each of these intermediate points is now going to be transformed again, and this is going to be the effect of capital B. Okay, so now we're gonna take a look at the effect now of capital B, which is equal to positive 1. If you notice, all of a sudden all the values of capital A, capital B, C, and D popped up at the top of the screen. I figured that I should include those on this slide as I'm working through the transformations. Now let's go ahead and write down the 4 new points that we're going to get. If we go back to the first page, If you look at step 3, it says that we're going to shift absolute value of b units right if the value of b is greater than 0. Okay, so we're going to be shifting right, and since capital B is greater than 0 and we want to shift right, we're going to add 1 to all of the x coordinates. Another thing you want to notice is if you look at the form of g of x here, so let me circle that for everybody. Okay, so if you look at g of x here, you're going to notice that in the parentheses, let me get a new color, you're going to notice here in these parentheses you have an x minus 1. Okay, so if you notice, whenever you have a minus sign inside of those parentheses, x minus some value, you're always going to be shifting to the right. If you happen to see a plus sign there, that's usually going to tell you you're going to be shifting to the left. That's why, as I noted in class, sometimes what I call these inside transformations, these transformations that affect only the x coordinates, it can be kind of counterintuitive, especially with when you compare it to how the vertical transformations work. Okay, so back to transforming these 4 intermediate points. Now that b is equal to positive 1, that means that we are going to add positive 1 to all the x coordinates. Again, we are not going to change or alter the y coordinates, because at this point we have only been working with horizontal transformations, and horizontal transformations only affect the x coordinates. Okay, so let's go ahead and add 1 to all these x coordinates. This top point is going to become 2 comma minus 2. If we add 1 to the x-coordinate of this point, we are going to get the point 1 comma 2. If we add 1 to the x-coordinate of negative 1 comma 1, you are going to get 0 comma 1. And if we add positive 1 to this last point down here, the new resulting point is going to be minus 1 comma 1. Okay, now when handling c equals 2, going back to the first page, if you look at step 4 down here, so first of all, the given f of x, the graph of y equals c times f. Okay, so our value of c was positive 2. And if you look at step 4, now that we've done our first 3 steps, step 4 says that we should scale the graph vertically by a factor of absolute value of c. Okay. This time, that just means that we have to multiply all of the previous y coordinates by the absolute value of c. However, if c also happens to be less than 0 or negative, we are going to follow the scaling by a vertical reflection. Okay, so this time c is positive, so we only have to worry about a vertical scaling by a factor of absolute value of c. Okay, so now, coming back to this slide, now that we know our c is equal to positive 2, again, if you go to the previous page, if you look at this number, positive 2, right here in front of f, that's our value of c. Okay, and since that's a positive 2, we are now going to multiply all of our y coordinates of those 4 points by positive 2. Okay, and then you should have just seen the 4 resulting points pop up on the right. So if you look here at this set of points, look at all the y coordinates, negative 2, 2, 1, and 1. Multiply that first y value, negative 2, by 2, and you get the resulting point 2 comma minus 4. The point 1, 2 is going to become the point 1, 4. The point 0, 1 is going to become the point 0, 2, and the point minus 1 comma 1 becomes the point minus 1 comma 2. Okay, and now for the last transformation factor, capital D, that's equal to positive 2. We can come back to the previous slide here. Okay, so where am I getting that D equals positive 2? You will notice if you look at this last value that you're adding outside of the parentheses on the function notation, that's going to be our capital D right here. Okay, so we're going to take those 4 resulting points that we obtained after applying the transformation factor capital C, and what we're going to do is we're going to add 2 to all of our y coordinates. Okay, whenever d is positive, you're going to add that value. Well, you're always going to add the value of d to the y coordinates. Okay, it's whenever in this case d ends up being positive 2, so we're going to add that to all the y coordinates. The 4 resulting points, I'm just going to write them down here at the bottom of the slide. So the first point, -2, -4. So this point right here. Applying d equals 2 is going to give us the point 2, -2. And the next point here, 1, 4. If you're looking at those previous values, that's going to become the point 1, 6. And the point 0, 2. We add 2 to the y coordinate, that becomes the point 0, 4, and finally we add -1, 2 to the point -1, 2. We're going to add 2 to the y coordinate and get -1, 4. Now, I wrote these points in order. We should make sure that when you transform some points, like in our graph, and the points are connected by line segments, you'd want to keep track of which points were connected to which other points. So if you look on the left, right before we applied a equals -2, you'll notice these first 2 points were connected, these points were connected, and these points were connected to each other. And it's going to be the same with these new resulting points down here at the bottom. Okay, these first 2 are connected, these 2 points are connected, and these 2 points are connected to each other by line segments. Okay, so there are our 4 points on the graph of G that we obtained after applying the series of transformations to the graph of F. Okay, so plot the point 2, -2. I'm using orange to plot the graph of G. Then we're going to plot the point 1, 6. So go right 1 unit from the origin and go up 6 units. 1, 2. Okay, so there's the point 1, 6. Then we have to plot the point 0, 4. So from the origin go up 4 units. And finally the point -1, 4, so go left 1 unit and up 4 units. And then the graph of G, the point 2, -2 is connected to the point 1, 6 by a line segment. 1, 6 is connected to the point 0, 4, and the point 0, 4 is connected to the point -1, 4. Now you'll have to forgive my artistry skills here, but there's what the graph of G is going to look like. You can essentially see the same basic shape. You should be able to see the reflection. These 2 points over here got mapped to these 2 points over here, so they got reflected over the y-axis at some point, and then you'll see this line segment right here got transformed into, well, let me clean this up a little bit actually. So let me do that again. These 2, oops, my bad. So these 2 points were transformed into these 2 points, and if I switch colors, okay, this line segment right here got transformed into this line segment right here. Okay. Alright, but there's the graph of G. So what we would like to do next, this kind of gives us an idea of what these transformations are doing to points on our graph of a function. What we would like to do next is, what if we're given a function algebraically by some equation, and we would like to apply some transformations to that function and know what the algebraic form of the resulting transformed function is. So that's where we're going with our next example, so bear with me just a moment. Okay, so here we go. Here's a blank whiteboard for us to work with, and what we're going to do here, this is going to be example 2. Okay, and what we're going to do is, okay, again, so this is going to be example 2, and what we're going to do is, let's actually start with a linear function and see what happens when you transform a linear function. So let's let f of x equal 2x plus 1. Okay. So start with f of x equals 2x plus 1. Okay, so for example 2, let's take a linear function, f of x equals 2x plus 1. Let's find an algebraic form of a function g whose graph is obtained from the graph of f by, so first we're going to horizontally stretch by a factor of 2. So before I even start reading the next steps, I'm just going to work on my capital A, capital B, capital C, and capital D. Okay, so if we come back to the first slide, if you look up here inside of these parentheses here at capital A, so you have c times f of capital A then times x minus b. Step 1 is you want to scale horizontally by a factor of 1 over the absolute value of a. Okay, so this is where whatever your scaling factor is, that means a is going to be its reciprocal. Okay, so back to the slide we were working on, back to our example. since it says we are horizontally stretching by a factor of 2, that horizontal stretch factor of positive 2 is going to tell us that capital A is going to be its reciprocal 1/2. Okay. Now the next step says we're going to be shifting left 2 units. And when we shift left 2 units, that means that our capital B actually has to be a negative value. Okay, so capital B is going to equal -2. The next step tells us that we are going to vertically compress by a factor of 1/2. Now that we're on the vertical transformations, whatever the stretch or compression factor is, in this case the vertical compression factor is 1/2, that's just going to be our value of c. And finally, the last step, shifting the graph of f up 4 units, that's giving us our capital D. When we're shifting up 4 units, D is going to be positive, so in this case we're going to want to let D equal +4. Now, using function notation, our next step is we would like to write g of x in terms of f using our capital A, capital B, capital C, and capital D. So g of x then is going to be 1/2, that's our value of c, times f of A, which is 1/2, times x minus b. Now when you subtract a -2, what's going to show up inside the parentheses is actually a +2, and we're going to add capital D, which is a +4. Okay, so we've got the expression for g of x now on the left. We've got our a of 1/2, our b of -2, our c of 1/2, and our d of 4. On the right hand side we have the definition of the function f. F of x is 2x plus 1. So the function f is telling us to take our inputs, multiply them by 2, and then add 1. So the first step here is somewhat recalling what we did back in section 1.4. So if you look at just the f of 1/2 times x plus 2, That 1/2 times x plus 2 inside of the parentheses, that can be thought of as a function composition, where we're composing f with 1/2 times x plus 2. So like we did in section 1.4, we're just going to evaluate this just like we would for a function composition. And what we're going to do is, in the expression for f of x on the right, notice we're going to replace this x on the left with 1/2 times x plus 2, so we're going to replace this x on the right as well with 1/2 times x plus 2. Now, before I actually plug that 1/2 times x plus 2 in for x, I'm going to actually distribute through the 1/2 and simplify what's inside of those parentheses real quick. Okay, and then when I do that, the inside of the parentheses, you're just going to get a 1/2 x plus 1. Now that becomes my input. Again, what we do is, if you look at the definition of f, we take our input and multiply it by 2, and then after that we add positive 1. Okay, so once I've plugged in my f of 1/2 x plus 1, which I have boxed in green, I just took 2 times that 1/2 x plus 1 and then added 1 as f tells you to do with inputs. And then inside of those brackets now, I'm going to have to simplify, so I'll distribute that positive 2. And distributing that positive 2 into the 1/2 x plus 1 gives us x plus 2. We're going to turn around and then add positive 1 to that. So you get x plus 3 inside of those brackets, which leaves us with 1/2 times x plus 3 in parentheses, and then plus 4. And then the last thing here is to just distribute the 1/2 and add like terms. And finally, in fully simplified form, the slope-intercept form of g of x, notice that that does end up being the equation of a line, 1/2 x plus 11/2. In the previous step, I distributed the 1/2, so I got 1/2 x plus 3/2, and then I added the 3/2 to the 4, getting a common denominator to get the 11/2. So ultimately, when we're done, g of x is equal to 1/2 x plus 11/2. So notice that, again, we started with a function f of x, which was 2x plus 1. That was a linear function. We applied a series of transformations and got the algebraic form of g of x, which again happened to be the slope-intercept form of a line. So as we saw in the previous graphing example, line segments got transformed to line segments. The same would be true of an entire line. Transformations transform linear functions into linear functions. Okay, so one more example. Suppose this time we're just given a function f of x, and we don't actually have the algebraic form, but we want to describe the transformations that are needed to transform the graph of f into the graph of g of x equals -2 times f of x plus 4 minus 7. So the first thing that we're going to want to do here is, if we look at the expression for g of x, that is the transformation form, and we want to identify the a, b, c, and capital D first, and then once we identify those values, we can follow our steps, the steps involved in a transformation, to describe those steps in order. So first of all, this value in front of capital F, the -2, that's going to be our C. Inside of the parentheses we have an x plus 4. This means that we take the opposite sign. Our value of b is going to equal -4. Now, it was foolish of me, but I did skip writing down what the value of capital A was. Notice there is no factor being multiplied by the x plus 4 inside of the parentheses. So what that tells us is A is going to just equal positive 1. The simple story for that is that since A is equal to positive 1, that means that there's no horizontal scaling and there's no horizontal reflections taking place. And then finally, the negative 7 that we're subtracting from the function notation, if you give my dog a moment here, just a moment, I gotta get my dog put away because he's barking like crazy. So this negative 7 that we're subtracting from f of x plus 4, that's going to give us a value for capital D of minus 7. So there's the capital A, capital B, capital C, and capital D that we're going to use to, that we would use to transform the graph of f. So on this slide I've copied the values of A, B, C, and D from the previous slide. We're going to use these values to describe the series of transformations. Since the value of A, capital A, is equal to positive 1, that means that we are neither going to horizontally scale this function. We're also not going to have a horizontal reflection. So we can skip right to B equals minus 4. And B equaling minus 4 is going to tell us that we're first going to shift the graph left 4 units. Next, since the value of capital C is negative 2, we can for now ignore the negative sign. That's going to tell us to vertically scale by a factor of 2. Graphically, this would mean we would multiply all the y coordinates by positive 2. And also, so we ignored the negative in that second step and scaled by a factor of 2. In this next step, we're going to recall that C was negative 2. Since that is less than 0, we're going to follow the vertical scaling by a reflection over the x-axis. I should also make a note up here. I shouldn't have written vertically scale here. If the absolute value of C is greater than 1, we should really be doing a vertical stretch by a factor of 2. And again, since C is negative, the next step would be to reflect over the x-axis. Okay, so if I was following the transformation with the graph of f, the first thing we would do is shift all the points on the graph of f left 4 units. And then vertically stretching by a factor of 2 says that we should multiply all the y coordinates by 2. If C is less than 0, reflecting over the x-axis is the same as multiplying all your y coordinates by minus 1. And finally, with D equaling negative 7, since that's a negative value, we will be shifting down. So finally, the last step with D being negative 7, we are going to shift the graph downward 7 units. So again, A was equal to positive 1. That meant that there was no horizontal scaling, and there was also no horizontal reflection. Capital B equaling minus 4 told us we should shift the graph left 4 units. C equals negative 2. We first ignored that negative sign, and that told us to vertically stretch by a factor of 2. So you would want to multiply all the y coordinates by 2. And then we recalled that C was negative, less than 0, so we followed the stretching by a reflection over the x-axis, and finally D equals negative 7 tells us to shift downward 7 units, which would be to subtract 7 from all y coordinates on the graph. With lots of practice, you can get to a point where you don't need to write the values of capital A, B, C, and D. You can come back to looking at the way that g of x is defined, and you should be able to just look at this algebraic form and be able to identify the transformations directly from that. However, when you're first learning, make sure that you're writing down the value of capital A, capital B, capital C, and capital D. When we come back to class tomorrow, which would be on Thursday, make sure that you again watch this video. I want to apologize for some of the recording mishaps that occurred halfway through the video. As I record more and more of these videos, hopefully it should be a little more fluid and I shouldn't have as many mistakes, but thank you for watching, and I look forward to seeing everybody in class. Have a good evening.